Start streaming. Oh my God. English caption okay na.
Kanina nakapag-generate ka ng transcript eh.
Ay, tama ba? Dahil monitoring page?
Oo, tinignan ko.
Kasi ito, hindi nagla-live kanina. Oo nga, kung bakit.
Pero kanina, ganito din yung ginawa mo.
Ganyan din.
Mukhang ako offline pa.
Saan ba yung YouTube ko? Ayaw nga nyo mag-live stream. Ayaw kung bakit.
Pero kanina, anong ginamit mo?
Yan. Low. Mic test. Gano'n nag-echo? Ba't nga nag-echo?
Ano nga, play ka ng video, yung black holes ulit.
Low, mic test. Oh my God. Zoom.
Pero kanina, anong ginamit mo?
Yan. Low. Mic test.
Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the star collapses into a black hole, mostly hydrogen atoms of black hole. What you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to tremendous amount of energy. In other words, it's impossible in the form of radiation. We just see a black sphere reflecting, maintaining a delicate balance between the two forces. Is the black part, as long as there is fusion in the core part, a star remains stable enough. The singularity for stars with way more mass than our own Sun, the heat singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space. Unlike all the elements that went before, the fusion process that creates iron right now doesn't generate any energy. It's
Iron
like a
builds up
dividing
at the
by
center
zero
of the star
error.
until it reaches
By the
a
way,
critical
black holes
amount,
do not
and the
sum
balance
things up
between
like a
radiation
vacuum
and
cleaner.
gravity
If we
is
were to
suddenly
swap the
broken.
sun for an equally
The
massive
core
black hole,
collapses
nothing much
within
would change
a
for us,
fraction of a
except
second.
that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. One, you die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014 plus 81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty. This is not the end of our story. There are loads more interesting ideas about black holes. We'll explore them in part 2. A big thanks to Fraser Kane for help with this video. By the way, we've made some Kurzgesagt wallpapers in 4K for different screen sizes. You can get them on our Patreon page, which also helped us to make more videos. Like this December, the first month ever with 3 videos. What is the true nature of the universe? To answer this question, humans come up with stories to describe the world. We test our stories and learn what to keep and what to throw away. But the more we learn, the more complicated and weird our stories become. Some of them so much so that it's really hard to know what they're actually about. Like string theory, a famous, controversial and often misunderstood story about the nature of everything. Why did we come up with it, and is it correct, or just an idea we should chuck out? To understand the true nature of reality, we looked at things up close and were amazed. Wondrous landscapes in the dust, zoos of bizarre creatures, complex protein robots, all of them made from structures of molecules made up of countless, even smaller things, atoms. With 3 videos. We thought they were the final layer of reality until we smashed them together really hard and discovered things that can't be divided anymore: elementary particles. But now we had a problem. They're so small that we could no longer look at them. Think about it. What is seeing? To see something, we need light, an electromagnetic wave. This wave hits the surface of the thing and gets reflected back from it into your eye. The wave carries information from the object that your brain uses to create an image. So you can't see something without somehow interacting with it. Seeing is touching, an active process, not a passive one. This is not a problem with most things. But particles are very, very, very small. So small that the electromagnetic waves we use to see are too big to touch them. Visible light just passes over them. We can try to solve this by creating electromagnetic waves with more and much smaller wavelengths. But more wavelengths means more energy. So when we touch a particle with a wave that has a lot of energy, it alters it. By looking at a particle, we change it. So we can't measure elementary particles precisely. This fact is so important that it has a name: the Heisenberg uncertainty principle, the basis of all quantum physics. So what does a particle look like then? What is its nature? We don't know. If we look really hard, we can see a blurry sphere of influence, but not the particles themselves. We just know they exist. But if that's the case, how can we do any science with them? We did what humans do and invented a new story, a mathematical fiction. The story of the point particle. We decided that we would pretend that a particle is a point in space. Any electron is a point with a certain electric charge and a certain mass, all indistinguishable from each other. This way, physicists could define them and calculate all of their interactions. This is called quantum field theory and solved a lot of problems. All of the standard model of particle physics is built on it, and it predicts lots of things very well. Some quantum properties of the electron, for example, have been tested and are accurate up to 0.0000000000002%. So while particles are not really points, by treating them as if they were, we get a pretty good picture of the universe. Not only did this idea advance science, it also led to a lot of real-world technology we use every day. But there's a huge problem: gravity. In quantum mechanics, all physical forces are carried by certain particles. But according to Einstein's general relativity, gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage. To put it simply, gravity is a theory of geometry, the geometry of space-time itself, of distances which we need to describe with absolute precision. But since there is no way to precisely measure things in the quantum world, our story of gravity doesn't work with our story of quantum physics. When physicists tried to add gravity to the story by inventing a new particle, their mathematics broke down. And this is a big problem. If we could marry gravity to quantum physics and the standard model, we would have the theory of everything. So very smart people came up with a new story. They asked, what is more complex than a point? A line or a string? String theory was born. What makes string theory so elegant is that it describes many different elementary particles as different modes of vibration of the string. Just like a violin string vibrating differently can give you a lot of different notes, a string can give you different particles. Most importantly, this includes gravity. String theory promised to unify all fundamental forces of the universe. This caused enormous excitement and hype. String theory quickly graduated to a possible theory of everything. Unfortunately, string theory comes with a lot of strings attached. Much of the maths involving a consistent string theory does not work in our universe with its 3 spatial and 1 temporal dimensions. String theory requires 10 dimensions to work out. So string theorists did calculations in model universes, and then tried to get rid of the 6 additional dimensions and describe our own universe. But so far, nobody has succeeded, and no prediction of string theory has been proven in an experiment. So string theory did not reveal the nature of our universe. One could argue that in this case, string theory really isn't useful at all. Science is all about experiments and predictions. If we can't do those, why should we bother with strings? It really is all about how we use it. Physics is based on maths. 2 + 2 makes 4. This is true no matter how you feel about it. And the maths in string theory does work out. That's why string theory is still useful. Imagine that you want to build a cruise ship, but you only have blueprints for a small rowing boat. There are plenty of differences: the engine, the materials, the scale. But both things are fundamentally the same: things that float. So by studying the rowing boat blueprints, you might still learn something about how to build a cruise ship eventually. With string theory, we can try to answer some questions about quantum gravity that have been puzzling physicists for decades, such as how black holes work or the information paradox. String theory may point us in the right direction. When used in this spirit, string theory becomes a precious tool for theoretical physicists and help them discover new aspects of the quantum world and some beautiful mathematics. So maybe the story of string theory is not the theory of everything. But just like the story of the point particle, it may be an extremely useful story. We don't yet know what the true nature of reality is, but we'll keep coming up with stories to try and find out until one day, hopefully, we do know. This video was supported by the Swiss National Science Foundation and realized with the scientific advice of Alessandro Sfandrini. What is the true nature of the universe? To answer this question, humans come up with stories to describe the world. We test our stories and learn what to keep and what to throw away. But the more we learn, the more complicated and weird our stories become. Some of them so much so that it's really hard to know what they're actually about. Like string theory, a famous, controversial and often misunderstood story about the nature of everything. Why did we come up with it, and is it correct or just an idea we should chuck out? To understand the true nature of reality, we looked at things up close and were amazed. Wondrous landscapes in the dust, zoos of bizarre creatures, complex protein robots, all of them made from structures of molecules made up of countless, even smaller things, atoms. We thought they were the final layer of reality until we smashed them together really hard and discovered things that can't be divided anymore: elementary particles. But now we had a problem. They're so small that we could no longer look at them. Think about it. What is seeing? To see something, we need light, an electromagnetic wave. This wave hits the surface of the thing and gets reflected back from it into your eye. The wave carries information from the object that your brain uses to create an image. So you can't see something without somehow interacting with it. Seeing is touching, an active process, not a passive one. This is not a problem with most things. But particles are very, very, very small. So small that the electromagnetic waves we use to see are too big to touch them. Visible light just passes over them. We can try to solve this by creating electromagnetic waves with more and much smaller wavelengths. But more wavelengths means more energy. So when we touch a particle with a wave that has a lot of energy, it